Molar conductivity is equal to conductivity multiplied by volume of solution containing 1 mole of electrolyte. On dilution, what happens? Conductivity decreases and volume of solution increases. Now this increase in the volume of solution compensates for the decrease in the conductivity, and overall the molar conductivity increases with dilution. So overall there is increase in the molar conductivity with dilution because of the increase in the volume of the solution. So this factor, that is increase in the volume of solution with dilution, dominates. Now conductivity is also equal to conductance multiplied by cell constant. Putting the value of conductivity in this equation of molar conductance is equal to conductance multiplied by cell constant multiplied by volume of solution containing 1 mole of electrolyte. Therefore, molar conductivity is equal to conductance of a solution which is kept between electrodes of a conductivity cell which are unit distance apart but having a cross section area large enough to accommodate sufficient volume of solution that contains 1 mole of the electrolyte. When concentration approaches 0 or at infinite dilution, the molar conductivity is known as limiting molar conductivity, and it is represented by lambda naught m. Limiting molar conductivity or molar conductivity at infinite dilution is the molar conductivity when the concentration approaches 0. Concentration of the electrolyte in the solution approaches 0. The variation of molar conductivity with concentration is different for strong and weak electrolytes. Now in this graph, variation of molar conductivity with dilution for both weak electrolyte, that is acetic acid, and strong electrolyte, that is KCl, is given. On y-axis molar conductivity, on x-axis square root of concentration. Now as can be seen for the strong electrolyte, that is KCl, the graph of KCl obeys the equation of line, that is y is equal to mx plus c. Graph of KCl can be extrapolated, and when it is extrapolated, it cuts the y-axis at a point which gives the molar conductivity at infinite dilution or the limiting molar conductivity. As far as graph of acetic acid, that is weak electrolyte, is concerned, it cannot be extrapolated because this is a curve and it can be seen that the graph of acetic acid is almost parallel to the y-axis. So it cannot be extrapolated to get the limiting molar conductivity. Therefore, to get the molar conductivity at infinite dilution for weak electrolytes, Colorocious law is used. One more information that can be obtained from this graph is, let this be concentration C2 raised to the power half and this concentration C1 raised to the power half. C2 is greater than C1. Therefore, going from C2 to C1, the concentration of electrolyte in the solution is decreasing or dilution is increasing. Now the value of molar conductivity corresponding to C2 for acetic acid, let it be lambda m1, and value of molar conductivity corresponding to concentration C1 of acetic acid, let it be lambda m2. Similarly, value of molar conductivity corresponding to concentration C2 for KCl, for acetic acid, this will be lambda m2 and this will be lambda m1. For KCl, value of molar conductivity corresponding to concentration C2 will be lambda m dash 2, and corresponding to concentration 1, it will be lambda m dash 1. Now for acetic acid, it can be seen that lambda m1 minus lambda m2 is greater than lambda m1 dash minus lambda m2 dash. Lambda m1 dash minus lambda m2 dash gives the change in molar conductivity with dilution for KCl. Lambda m1 minus lambda m2 gives the change in molar conductivity with dilution for acetic acid. Now it can be seen that the molar conductivity of weak electrolyte, that is acetic acid, it increases very fast with dilution, whereas the molar conductivity of a strong electrolyte like KCl increases very slowly with dilution. The reason is, why is acetic acid called weak electrolyte? Because when it is dissolved in a solvent, it dissociates to a very less extent. But on dilution, its degree of dissociation increases. More and more acetic acid molecules dissociate into its ions, as a result of which its molar conductivity increases. Whereas KCl, which is a strong electrolyte means it is 100% dissociated at all dilutions. The moment KCl is dissolved in a solvent, it dissociates into its ion, and the dissociation is 100%. So, degree of dissociation of KCl is not affected by dilution. Therefore, molar conductivity of weak electrolyte increases very fast with dilution, and molar conductivity of a strong electrolyte increases slowly with dilution. For strong electrolytes, molar conductivity increases slowly with dilution and can be represented by the equation molar conductivity is equal to molar conductivity at infinite dilution or limiting molar conductivity minus A into square root of concentration. It can be seen that if we plot molar conductivity against square root of concentration, we obtain a straight line with intercept equal to limiting molar conductivity and slope equal to minus A. The value of constant A for a given solvent and temperature depends on the type of electrolyte, that is, the charges on the cation and anion produced on the dissociation of the electrolyte in the solution. For example, NaCl, CaCl2, MgSO4. For these electrolytes, if the solvent is same, temperature is same, then the value of A for this electrolyte will depend upon the charges on the cation and anion produced on the dissociation of these electrolytes. For example, NaCl dissociates to give Na plus and Cl minus ion. Charge on cation +1, charge on anion -1. So what kind of electrolyte it is? It is 1 - 1 or 1 type electrolyte. Calcium chloride dissociates to give Ca2 plus and 2Cl minus. Each calcium ion has a +2 charge and each chloride ion has -1 charge. So the type of electrolyte is 2 - 1 or 2,1 type electrolyte. Magnesium sulfate dissociates to give Mg2 plus and SO4 2 minus ion, magnesium ion +2 charge and sulfate ion -2 charge. So the type of electrolyte is 2 - 2 or 2,2 type electrolyte. Now all the electrolytes of the type 1,1 or 1 - 1 will have the same value of A. All the electrolytes of the type 2 - 1 or 2,1 type will have the same value of A, and the electrolytes of the type 2 - 2 or 2,2 type electrolytes will have the same value of A. So it can be seen that the value of A depends upon the type of electrolyte, which in turn depends upon the charge on the cation and anion produced on the dissociation of the electrolyte.